Let's now analyze our linearized equations of motion precisely. And the main message that we're going to learn is that the flows near the fixed point are determined by the eigenvalues and eigenvectors of the linearized transformation matrix A. That is, in our linearized equation of motion, we had epsilon dot was equal to A epsilon, where A was the matrix A, B, C, D. And as we're going to see, the eigenvalues and eigenvectors of this matrix determine everything. Now, it's a simple exercise in linear algebra to find the eigenvalues of this matrix. Lambda plus minus are the two eigenvalues. They're equal to 1/2 t plus or minus a square root of t squared minus 4d. Where in this formula, t is the trace of A, and it's equal to the sum of the diagonal elements, A plus D. And D is the determinant of the matrix A, and that's just equal to AD minus BC. Also, the eigenvectors associated with each eigenvalue are epsilon plus minus. And because we're dealing with a linearized transformation, we don't have to worry about the normalization of the eigenvector. All we care about is just the direction that it's pointing in. And so we can write this generally as the column vector 1 in the first entry and lambda plus minus minus A divided by B. So how does these determine the local flow? And the main point is that if we're given any vector r that's lying in this two-dimensional linearized state space, it can be decomposed as A plus epsilon plus A minus epsilon minus. As long as the eigenvectors are not parallel, which is generally not the case, then it spans a two-dimensional space, and any arbitrary point in that space can be decomposed as a linear combination of the two eigenvectors. And then r of t is just given by A plus epsilon plus e to the lambda plus t plus A minus epsilon minus e to the lambda minus t. And so this determines fully the local flow near a fixed point. And the crucial issue, as we're going to see, is that the nature of the fixed point is determined by the actual values of the eigenvalue.